Well, the sequence given by these recurrence relations, quite interesting, u2n and u2n plus 1. And there's other information given, k, p, and q positive constants, pq not equal to 1. Write down the first 6 terms of the sequence. So actually we've got the first term, it's just k. Then the second term is going to be when we can put n equal to 1 into here. So it'll be u2 is u1 times p. So it's simply going to be pk. For u3, I can put n equal 1 into here. Then it's going to be u2 times q. So it will be pqk, or qpk, however you want to write it. And we can just keep going. So now let n equal 2 in the middle one. That would mean it's u3 times p, so it's going to be times by another p. So p squared qk. u5, 2 into the bottom one. So u4 times q gives p squared q squared k. And finally, u6, we're going to be times by p again. So p cubed q squared k. Those are our first 6 terms. So as we've identified, essentially every time we get a new odd numbered term, we're going to be timesing by an extra q. And then when we get a new even one, we're timesing by an extra p. And that pattern's going to continue. So for part B, we're summing all the terms up to 2n. Therefore, we're going to get k plus pk plus pqk, and so on. Write all of these down. Then that should be p cubed. The first thing I can do is just factorize the k out. So that's going to make life a lot easier. So I get 1 plus p, that'll be a bit easier to see then, plus pq, p squared q, and I can then try and split this into, I mean, there's a sort of geometric series going on. So on one hand, we've got the term 1, and then pq, and then p squared q squared, and then there would be a p cubed, q cubed. So I can write it as just like that. And then the other one, still got the k factorized out. Actually, this time I can also factorize out a p, because then I get 1, that comes from here. And over here, I've got pq, then this one here, pq squared, and so on. Okay, so nicely split it into these two. Both of these are geometric series, like the parts in the brackets, and they've got initial term 1. So, oh, sorry, that's right. A equals 1, and R is equal to PQ. So the sum to n, actually, it's going to be this. I forgot that actually. I forgot the last few terms. In fact, I don't need to write them down, but I can recognize that I've got 2n terms overall. So I've got n terms in this one and n terms in this one. So Sn is going to be a, just like the normal, 1 minus r to the n over 1 minus r. So I'm going to get k times a for us is just 1, so it'll be 1 minus pq to the n over 1 minus pq plus kp times the same thing. Let's just take a little look at what we're actually trying to get to. Trying to get to here. I think we're nearly there. Just going to bring it all together. So I can factorize out k plus kp. And then actually I can just times that by 1 minus pq to the n and put all of that over 1 minus pq. And now I just need to manipulate it a little bit more, take the k out, so 1 plus p. Sorry, let's just check how it was written here. And then, yeah, that's okay. And then 1 minus pq to the n all over 1 minus pq, which is what we wanted. Okay, nicely done. Takes us to the very last part, where we're given this is the floor function, I think. So whatever our number is, we basically take it down to the next lowest integer. Okay, let's write down a few terms for this. So I'm going to get 6 multiplied by 4 over 3 to the half. So I've taken the factor of 6 out, times, sorry, there should be a bracket there, times 3/5, and then I'm going to put 1 in just to the 0. I'll deal with this as I go along. So a half is actually going to go like round down to 0. So actually this just becomes 1, and this just becomes 1. So overall the term becomes 1. Second term, 4/3 to the 1, so that will stay. And then 3/5 to the half. Sorry, I should keep the floor function in there, but that's okay. And this one's going to become 3/5 to the 0. So again, it's going to disappear. Okay, let's keep going with a few more terms to get a feel for it. So then that was 1, 2, now we're doing 3. So 4/3 to the 3 over 2. Actually, this is simply just going to become 1. So I can just get rid of it. And then 3/5 to the 1 here. So I can get rid of that as well. And we start to see a pattern. So, it's not going up, not quite going up by, like sometimes we skip them and sometimes we include them. Let's just do another one. 4/3, then it's going to be 4 over 2 or 2 times by 3/5 to the 3 over 2. So again, that is just going to become 1. I can get rid of it. Okay, and this obviously continues. Let's just put it together. So I'm going to get 6, then 1 plus 4 over 3 plus 4 over 3 times 3 over 5 plus 4 over 3 squared times 3 over 5. Then on the next one, this would go up to 5 over 2, which would remain as 2 when we do the floor function, so it would be 4 over 3 squared. But then this one would end up being 2. And you can see we've got something very similar to what we had in part B, where we showed that this was true. So for us, K is 6, P is 4 over 3, and Q is 3 over 5. Therefore, this is going to equal 6 times 1 plus 4 over 3 times 1 minus 4 over 3 times 3 over 5 to the n. Oops, let me try that bit again. All over 1 minus 4 over 3 times 3 over 5. The only extra bit I have to put in, remember, we're actually doing a sum to infinity, so I need the limit as n approaches infinity. So the 4 over 3 times 3 over 5 just becomes 4 over 5. And as n approaches infinity, 4 over 5 to the n's actually going to approach 0. Essentially, you could use the infinity formula, which is just a over 1 minus r. You can cancel this bit out, but I'm kind of doing it from first principles. So it's going to become 6 times 1 plus 4 over 3 is 7 over 3, then times 1, because like I said, that term disappears. Then I'm going to be dividing by 1 minus 4/5. So that is going to be 42 over 3 all over 1/5. 3's into 42 go 14. So 14 over 1/5, which gives a final answer of 70. Really nice. Just want to kind of just very quickly summarize it. So we wrote down the expression with the floor function, or the integer part of x, so the same thing. Wrote it out, saw that a pattern is occurring, that justified to ourselves that that is going to continue in such a way as it did in part B. And we can identify it like this one here, you can clearly see it. Then wrote down the sum straight away using the result from part B, but that was the bit without the limit is when we're just summing up to 2n. So put the limit in as n approaches infinity. Checked that PQ in this case is going to tend to 0. You could alternatively, like I said, deal with the sum to infinity like this, but I've just put the limit in and use that idea. And then cancel things out as needed to give a final answer of 70.